The next thing now, we have to use some formulas. And these formulas are a bit frustrating for me because they have magic numbers in them. But nonetheless, we'll work with what we have here. And we'll notice here that to find our arcing current, we're giving a relationship here where we're given a formula with the log of our arcing current is equal to K plus 0.662 log the bolted fault current, which we just calculated, plus a term 0.0966 V, which V is our voltage in kilovolts, plus then another term which is a function of the gap between our conductors. In this particular example, we're going to be using 25 millimeters as our gap, then plus another term which is multiplied by our voltage and the log of our bolted fault current, subtracting another term which is a function of our distance times the log of our bolted fault current. Again, these seem to be rather obscure formulas. There's nothing we can directly relate to specific values. What I suspect about this rather is that these terms were derived through some comparison with experimental data to come up with a reasonably close curve fit to a number of statistical samples that they had of what type of energy did we typically get, or what type of arcing currents did we typically get for a variety of faults. So here I have an IBF of 19.9 Ka, and I'm going to see that I'm going to apply, so again I need a K plus 0.662 log IBF plus 0.996 V plus 0.00526 G plus 0.5588 V times the log of IBF minus 0.00304 G times the log of IBF. Don't worry, I will give you handouts of this. Now my K, let's just look at what some of the terms are here, because that becomes important. K is going to be equal to, K is either minus 0.153 if we're dealing with an open configuration, or minus 0.097 if we're in a box. See that the idea of whether we're in an enclosed space or whether we're out in the open has an impact on a number of calculations here. Our voltage V is going to be, again, we're on a 480 volt system, so that's going to be 0.48, and G again is the spacing between our conductors. Let's look at this formula just briefly to see a couple of things that we can understand about it. Here we're multiplying our bolted fault current by 0.662. Again, we're dealing in the log side, so we're taking a fraction of that current. Then you can see the terms that are going to add to it depending on our voltage, and subtract from it depending on our spacing. We're going to see we're going to come out with a number that's less than our specific value. If I go through here and I was to continue through this calculation, again with my K being minus 0.097 because we were in an enclosed space, V equals 0.48 and G equals 25. At the end of the day, when I go through and I solve for IA, what I got as a calculation in this particular case was 11.8 kiloamps. So it's less than my 19.9 Ka, but it's still a respectable current. Now that I have that, I need to find another term, which is my normalized energy. So again, you'll notice we're dealing with logs here, but I have a term here which represents my energy in calories, which is for term K1, which again is going to account for whether I'm in an open configuration or in an enclosure. I'm going to assume I'm in an enclosure. The second term gives me a value if I have resistance or no resistance in my system. IA again is my arcing current, and then I have my distance. You notice here this is taken from an example, but we'll find that our distance of 25 millimeters would be common whether we're dealing with a bus panel board. Our bus here most likely represents a panel board in a system. So if I write out now for my E sub n, I have minus 0.555 minus 0.113, and that is going to be plus 1.081 log, again I'm taking the log of IA now, plus 0.0011 G. So IA in this case was 11.8 Ka, G is 25 millimeters, and if I go through this calculation I get E sub n of 3.3 calories. because some references will actually show this as being in joules per centimeter squared. I'm not entirely sure. Again, because we have so many magic numbers here, we're not going to worry about too much about what our units are at this stage. The last step, once we found this normalized energy, is now we need to find our actual incident energy. And we have a formula here where we have our incident energy is equal to a calculation factor, which is a function of our voltage. We have T, our arcing time, D, our distance from the arc to the person, and you'll notice here that it's typical if we're dealing with panel boards or motor control centers to use 18 inches or 455 millimeters. X is a distant exponent that's given by the IEEE. For the systems we're dealing with, we'll see, again, this is information I'll give you in detail when you're working with this, but we deal with a factor of 1.641. So if we go through that calculation, we have E is equal to 1.5, that's our CF factor, since we're dealing with 480 volts, times 3.3, our normalized energy, times T over 0.2, times now 610 raised to the power of 1.64 over 455 raised to the power of 1.64. There's a lot of constants here that I can group together, and what I can see is that this is going to translate into, if I group the 1.5, 3.3, and this all evaluates out, this becomes 8.01 times T over 0.2. And this is in calories per centimeter squared. Now this is getting exciting. I'm having to hold myself back here because we've reduced this down now into an expression where we can see the real factor that I'm concerned about is the time that my arc is present. So how am I going to find that time? Let's take a look and see how we might do that. Remember that my arc is occurring at a current of 11.8 kiloamps as I've calculated it. So here on the time current curve, and the device that's got to clear that breaker, I've modified these slightly since the first video you looked at, but the device that's going to clear that fault is the high voltage circuit breaker. So I've dropped the crosshairs onto the time current curve here, and you can see that for a current of very close to the 11.8, I'm at 11,671 amps, the breaker will not clear that fault until 2.28 seconds have passed since that occurrence. So if we know that T is 2.28 seconds, then I should be able to go back in here and say that E now is 8.01 times 2.28 over 0.2, calculate this out, and I get E as being 91 calories per centimeter squared. Now, let's, for fun, go back now. Since we are dealing with ETAP, I should be able to see what ETAP actually tells me it thinks that value is. So I'm switching now to my short circuit mode. So the first thing I'm going to do is, again, I've faulted this bus. I'm going to get my short circuit current. You may remember we did this last day, and I'm seeing that it's giving me a bolted fault current or short circuit current of 19.47 kA. My estimation that I used, which I wasn't real happy about using, gave me 19.8 kA, so I'm reasonably close with my 60% estimation of my actual transformer short circuit. Now I can switch and actually have an arc flash analysis done according to IEEE 1584, and that's the small triangle button that we see here. So what it's done now is it's calculated out, again, this is where I got my arcing current from the first video. It's telling me that my arcing current here is 12.01 kA. So it's got a slightly higher current than what I had been using in my example. It's also treating this bus slightly differently than I may have been treating it previously. And it's coming up with an incident energy of 120 calories per centimeter squared, as opposed to the 91 calories that I calculate. Obviously, there can be a little more sophistication in the calculation that's done by the software. It's interesting that we came up reasonably close, and in fact, with some of the work that you're going to be doing later on, you may find that you get almost exactly the same results in your calculation. We're not limited simply to some of the circuits that we're dealing with or some of the systems that we deal with in ETAP. It's worth noting that the study or calculation of incident energy also expands out into other areas. If I'm looking at actual circuit breakers, there is actually a tabulation of the incident energy that's released when they are actually clearing a fault. It isn't always the most pleasant place to be around a large circuit breaker when it's dealing with a short circuit fault. So this is just a quick example to show you that the relationship between joules and calories, if we're given information in one form, that we can move it to the other. So in summary, we've done a brief introduction to the arc flash calculations. This is what's actually going to form the basis of the assignment that we're going to work through on Monday. And now I'd like you to join me in video number 3, where we're going to take a brief overview of arc flash mitigation strategies. Thank you.